Hi everyone, welcome to part 2 on our video lecture for section 12.3 on the calculus in polar coordinates. In part 1 of our video lecture, we went over how to find the slope of a tangent line to a polar graph. In this video lecture, we're going to be going over how to figure out points of intersection, which will prove crucial to determine the area of a region bounded by a graph of a polar curve. Alright, so I want to begin by mentioning here that finding points of intersection between polar graphs is not going to be as easy as finding points of intersection between two regular lines or curves in Cartesian coordinates. So, why is that the case? Well, we're going to be taking a look in this a couple of examples, but I do want to mention here that we will be using a combination of algebraic and graphic techniques to figure out these points of intersections. So let's take a look here at this example where we're trying to figure out the points of intersection in Cartesian form for the two graphs in polar coordinates r equals to negative cosine of theta and r equals to 2 minus 2 cosine theta. Alright, so for this one here, let's go ahead and begin by making a sketch. So let's go to our graphing calculator. Alright, so let's see. The first function was a negative 6 cosine theta. Now quick question, which shape is this one going to be? Well, we saw a couple of these examples in class last Tuesday, so you might get an inkling that, okay, yeah, this is going to be a circle, and you're right, this one here will be a circle. Now the second function here was a 2 minus 2 cosine theta. And what is the shape of this one? Well, this one here, as it turns out, is going to be a cardioid. And I believe we saw one in the previous section. Now this one, since both functions are dealing with a cosine, then we're going to have some shapes here that are basically towards the left-hand side of the x-axis. Now notice here when I click on graph, I was using a previous window setting. Now remember in class I mentioned that the quickest way to define a better window setting was just to use the zoom function. So I'm going to go to zoom here and go all the way to 0. And there we go. Now this one here, we know we're dealing with circles. They kind of look like an ellipse. So if you want, you can also just click on zoom here and click on zoom square. Oh, okay, it wasn't that better. I'm just going to go back to this window setting. I like it a little bit more. Okay, so now for this one here, I do recommend making a sketch. However, since I'm on OneNote, I'm going to take the opportunity of just attach the picture on the document. But normally though, I would recommend you guys to make a sketch. Actually, I will not recommend. I will have you guys make a sketch because making a sketch for this problem is going to be crucial. All right, so let's see. So here I have attached now my graph. All right, so the first thing that I want you guys to do here is to figure out the intersections algebraically. Now this one here is no different than figuring out intersections in the Cartesian coordinate system, where we just needed to set both equations equals to each other. So well, that's what we're going to be doing here. I'll take the negative 6 cosine theta and set it equals to r2 minus 2 cosine theta. Okay, now solving this one here, I think we can go ahead and add the 2 cosine theta to both sides. And this is going to give us here, let's see, a negative cosine theta equals to a 2, which we can go ahead and simplify further, and that's going to give us a cosine theta equals to a negative 1/2. Now this one here, you can go ahead and evaluate with the calculator, take a look at your unit circle. Doesn't matter, whatever you want to do, but the angles that give you a negative 1/2 for the cosine are a 2 pi over 3 and a 4 pi over 3. All right, now the question is, okay, well, I know that the intersection are happening when the angles are 2 pi over 3 and 4 pi over 3, but where exactly are they? Well, I'm just going to go back here to our graph, and I'm going to click here on the trace once more and select our angles. So where is the angle of 2 pi over 3? So 2 pi over 3. Let's see. Okay, well, it looks like the intersection on the top is the one that corresponds to the angle 2 pi over 3. So I'm just going to go ahead and mark it here on our sketch. So this one here is the 2 pi over 3. Now, where's the 4 pi over 3? Going back to our calculator, trace, where is the 4 pi over 3? And there we go. It's the bottom intersection. All right, so here we have the 4 pi over 3. Okay, now, are we done with the intersections? Well, you're probably wondering, wait, there's probably one, well, isn't there one more? And I would agree with you guys, there is actually one more intersection right over here. However, that point of intersection was not given algebraically. This one we actually calculated visually. All right, so taking a look at it visually, it happens to be at the pole. So I'll put here visually one more intersection at the pole. And again, remember the pole is just the origin in polar coordinates. Alrighty. So I'm going to go ahead and rewrite this intersection of the pole in Cartesian form because it's already pretty straightforward. So this one here is at the pole. It's located at the point 0, 0. Okay, now we do have more intersections here though. The one that's happening at the 2π/3. Now, since we do want the Cartesian coordinate system, I'll just go here and write the Cartesian coordinates, and let's go ahead and first do the intersection when the angle theta was 2π/3. All right, so we know that x is the same thing as r times cosine theta, and y equals to r times sine theta. So we just need to go ahead and evaluate that. Now, what is the r though? Well, at this point, since they do have the same r value or the same, well, you can see here that they're going to have the same y value and the same x value, it doesn't really matter which r you pick. Typically, I pick the easiest one. So the easiest one is, I would say that r equals to -6 cosine theta. So I'm going to pick this one here. Say here that r, in fact, I'll put it in a different color. I'm going to go for orange. Okay, so let's see, then the x value is going to be r. So what is the r when you evaluate it at the 2π/3? I'm going to put it here. So -6 times the cosine of 2π/3. Well, the 2π/3, if I'm not mistaken, is equals to a -1/2. So -6 times a -1/2 should give us a value of 3. So the x value then is going to be 3 times the cosine of 2π/3, which is equals to a -3/2. Now for our y value, well, the r value is the same. So we're still going to have a 3 times the sine of 2π/3, and that's going to give us the sine of 2π/3. Again, if you take a look at the unit circle, put in the calculator, it should be a rad3/2. So 3 times rad3/2 is going to be just 3 rad3/2. Okay, now let me make this a little bit smaller because I think I made my image too big. There we go. So now we figure out what are going to be the coordinates when the angle is 2π/3. The Cartesian coordinates are going to be a -3/2 and a 3 rad3/2. Now in the case for theta equals to 4π/3, we are going to be repeating the same process. So doing that, we're going to get r is the same thing as a -6 times the cosine of 4π/3, which is going to give us another +3. Now for x, we're going to have 3 times the cosine of 4π/3, which is equals to a -3/2 again. And for the y value, we're going to get 3 times the sine of 4π/3, which is equals to a -3 rad3/2. And this should give us our second intersection, or technically our third if we're considering the pole. So we're going to have here -3/2 and -3 rad3/2. And there we go. So this one's here, guys, are our 3 intersections that we're observing between the 2 curves. Now, as you can see here, again, if you're solving them algebraically, you may not get all of the intersections. Sometimes you have to visually inspect the curves so you can see, okay, well, am I actually getting all of the intersections? And again, a lot of times you will see 1 or 2 that are not given algebraically. All right, so let's take a look at another example here. Now this one, we're trying to figure out, okay, what will be the points of intersection in Cartesian form for the graph of the function r equals to 1 plus sine theta in polar and r equals to 1 minus sine theta. All right, so for this one here, I'll let you guys start to sketch it. So pause the video and make a sketch. See what kind of curves are we going to be getting. Welcome back. So hopefully your sketch looks something like this graphs, where we have essentially 2 cardioids that are overlapping. All right, so let's see if we can go ahead and find out the points of intersections. So once more, let's go ahead and begin by finding them algebraically. So we're going to be setting both functions equals to each other. So we're going to have 1 plus sine theta equals to 1 minus sine theta. Now for this one here, we see a +1 on both sides of the equation. So I'm going to go ahead and cancel it out and add a sine theta to both sides of the equation. So this would lead us to getting an equation 2 sine theta equals to 0. So we're just looking then for the solutions where sine of theta is equal to 0. And the only angles where theta is going to be equal to 0 between 0 and 2 pi are just going to be 0, pi, and 2 pi. But to be honest, the 2 pi is just taking you back to the same place. So it's just going to be 0 and pi. Alrighty. Now where are these points located in the graph? Once more, we can just go to our calculator, click trace, and let's see. Where is the point located, or where is the point that's associated with the angle theta equal to 0? So I'll just put here 0, and there we go. It seems like it's the location on the right. So the right-hand side intersection is the one that's associated with theta equal to 0. Now, as you might expect, the one on the left is going to be the one that's associated with theta equals to pi, but lo and behold, once more, we have an issue. What about this intersection? So this one here is not represented with the algebraic solution. So once more, I'm just going to go ahead and write down here visually. We have the intersection at the pole, and this one here is located at, well, I'll put here, which is just going to be the point at 0, 0. Okay. There we go. Now, let's see, okay, well, what are going to be the points in the Cartesian coordinate system? Well, let's see, the first one that's associated with theta equals to 0, it's going to be given by, let's see, now, again, it doesn't really matter which R you pick, guys, so I'm just going to go ahead and pick, I don't know, the 1 plus sine theta. So I'll write it here, R equals to 1 plus sine theta, and when theta is equals to 0, then we just get to see here that the R value is equals to 1. All right, so then for our X coordinate and our Y coordinate, this time around, guys, I will let you finish them, but I do want you to verify that the Cartesian coordinates that we should be getting are going to be 1, 0 and -1, 0. Again, I want you guys to verify it, and you can just verify it by knowing that X equals to R times cosine theta, and Y equals to R times sine theta. Okay. Now, before we go ahead and cover new topics, I do want to give more clarification for why we're not getting all of the intersections algebraically. The reason for that is because even though you might reach the same Y values, you're not reaching the same Y values in the same values for theta. An easy way of understanding this is to, rather than thinking about the equation in polar form, let's say that we're dealing with parametric equations, and let's say that we're dealing instead with 1 plus sine of t and 1 minus sine of t. And let's say that these ones here are sketching the curve or the path that a particular particle is taking. Now, as the particle moves around in time, it is going to be tracing the graph, but the thing is though, the graphs are intersecting at the pole here, but they're not really crossing each other in the same time. And the paths may not cross each other because, well, maybe the particles are moving in different directions, as we saw with parametric equations. Direction didn't matter. So they might start in different locations as well. So a couple of things could happen. Now, sure, their paths may cross, but they're not crossing at the same time. When we're solving them algebraically, we're actually saying if they cross during the same time, but that's it. We're not saying, okay, they're never crossing at some other time. So that's why it's important to graph them to visually see if there are any more intersections. Okay, with that said, we're going to be taking a look at another topic here that is going to be related to the points of intersection. And this one here is the area that's bounded by a polar graph. So how do we figure out the area that's bounded by the graph of a polar curve? Well, lucky for us, we're going to be using the same ideas that we used to figure out the area underneath the curve in Cartesian coordinates. So recall here that if we had some given curve, what we did here was to essentially use rectangles to approximate the area. Now, when we calculate the rectangles here, well, we needed to figure out what was the width of the rectangle, the delta x. Now, once we had the delta x, that was the width of a rectangle, and then we calculated the height of the rectangle by using either the left bound or the right bound to figure out the height for the rectangles. Now, in this case here, I'm using my left endpoint, and we got here, and let's go here for 4 rectangles, and there we go. So this one here, adding up the area of the rectangles, oops, actually 3 rectangles, then we could have approximated the area underneath the curve, but if we wanted to make it exact, we would need to add an infinite amount of rectangles. Well, with polar coordinates, it is going to be the same idea, except that rather than using the area of a rectangle, instead, we're going to be using the area of a sector for a circle. And this one here is given by 1/2 times the radius squared times theta. represented here. If I have some sector for a circle, the area is 1/2 times r squared times the angle theta. Now, as you might expect, well, we're not going to be dealing with just circles. Instead, we might be given some other shapes or some other curves or regions as represented here in this second image. Now, notice here that we're looking for the area that's bounded by two angles, theta equals to A and theta is equals to B. Now, how are we going to do it? Well, we're going to be partitioning this interval, not in rectangles, but again, in terms of sectors for a circle, or you can think of them as kind of like wedges here. Now, this one here will be our delta theta, and to figure out not the height, but instead the radius of the circle, well, as you might expect here, we're just going to be evaluating the function at some theta I. Now, this one here is represented or illustrated in the third figure. Now, note here, though, that with this delta theta here, it seems like we have a little bit of overestimation here, but that's okay because we were also getting overestimations here when we were doing the Riemann sums. We corrected this issue by adding more and more rectangles, so as you might expect in polar coordinates, we're going to be correcting this issue by adding more and more slices. Now, once we do that here, well, in fact, I'm going to do the approximation first here. The area is going to be given here by 1/2 times the sum as I goes from 1 to n for the function evaluated at theta I. It's going to give us a radius times our delta theta. Now this one here is giving us the approximation, but if we take the limit as n approaches infinity, we would be getting the exact area. And that's exactly what we have here. If f is a continuous non-negative function on the interval alpha to beta, where beta is greater than 0 and, well, b minus alpha is greater than 0, less than 2 pi, then the area for the region bounded by the graph of f of theta between the radial lines theta equals to alpha and theta equals to beta is given by the formula A is equals to 1/2 times the integral from alpha to beta for f of theta squared d theta, which could be abbreviated here by using r squared rather than the function f of theta. Alright, so again, this one here was giving us the approximation, but the integral here is giving us the exact area. Okay, so let's try a couple of examples here to get comfortable with the formula. But before I do though, I do want to mention something. Now, we were doing points of intersection right now. Well, as it turns out, point of intersection will be playing a crucial role when calculating the area. So, to determine the appropriate bounds for the integral, yeah, we're going to look for the points of intersection. However, well, I also want to mention that this problems could be made much easier if you use symmetry to set up the integrals. And I'll show you a couple of examples where we're going to be using symmetry to avoid some long, complicated problems. Okay, now the last thing that I want to mention here that this formula is only valid if f takes only either positive values or negative values. Again, we're going to be using symmetry to avoid complications. Alright, so without further ado, let's take a look at a couple of examples. Let's begin with the first one, where we're trying to figure out what is the area for one petal for the rose curve given by r equals to 3 sine of 2 theta. So let's take a look. Okay, so let's go ahead and begin by making a sketch to see what we're dealing with. So going to our calculator, and let's see, we're going to get 3 sine of 2 theta. So let's see, clicking on graph. Okay, no, the window here is a little bit off, so I'm just going to click here on zoom, fit, and there we go. Now we have here our rose curve with 4 petals. So we're interested in getting the area for only one of the petals, not all of them. So at this point, I'm going to ask you guys to make a sketch, but in my case, I'm just going to go ahead and attach the image. But if I ask you guys for this on the exam, I'll give you some grid or some graphing paper that you can use. But let's see, I'm just going to go ahead and attach the image and then proceed. All right, so there we go. We have the image attached. So now what do? Well, we're looking for the area for only one of the petals. So it doesn't matter which one we pick because, well, as you can see here, they are symmetric. So I'm going to go ahead and pick the first petal. And I want to figure out, okay, what is this area? Well, if we want to figure out the area, we need to know the area from what bounds. From what bound to what bound? Well, for this one here, then, it seems like we need to figure out what will be our point of intersection right over here. Now you get to see here that basically it seems like one of the petals is intersecting at the pole. So I'm just going to go ahead and set up our equation. R equals to 3 sine theta, sorry, 3 sine of 2 theta, and I'll set it here equal to 0. Now once we do here, it seems like the equation that we're trying to solve then is the sine of 2 theta equals to 0. So the question is here, okay, so the sine of what angle gives you 0? Welcome back. So this is the area that I got. The way to simplify this integral here was to recognize that, okay, well, we have a sine squared, so we need to use the half angle identities or the power reduction identities. Same thing, just different name. So we need to break this one, the sine squared, as 1 minus the cosine of twice the angle. So now it's cosine of 4 theta over 2, which, simplifying it here, whoops, and I do realize that I did miss my limits of integration. There we go. So this integral gave me a 9 pi over 8, or a 9 pi over 8. So there we go. This is the area for only one of the petals. Now here's the thing though. What if I wanted you guys to find the area for 2 of the petals? Well, since you know that they have the same area and they are symmetric, well, they are symmetric, so they have the same area. So we could just multiply our value times 2. If I wanted you to figure out the area for 3 petals, you would just multiply by 3, find the area for all 4 petals, get the area of 1, and multiply it by 4. Okay, so at this point, guys, I think this video is running a little bit long, so we're going to be stopping here, and we'll continue on with more problems in part 3. See you guys there.